So moving on, let's find the limits of sequences that involve polynomials and fractions of polynomials, okay? For example, by using large values of n, predict the limit of the sequence whose general term is 5n squared plus 6 over 7n squared minus 8. Say we use n equals to 1,000, we will actually get 5,006 over 6,999,992. Okay? So as n gets large, what do you think this will approximately equal to? Someone say it? 5 and 7. Yes, it will approximately equal 5 and 7. So for the following examples, our general approach will be to get the fraction with n squared, n cubed, etc. in the denominator, as those will shrink to 0, and then we can use limit notation to set this work out. So let's do 3 examples and see what we notice. I just realised, is anyone still writing? Yeah?
Can you just, as a tendency, in a term like that, when you have the addition or subtraction of a constant, can you just immediately assume you can ignore it because as n becomes larger and larger, that tiny difference becomes insignificant?
You can't always assume it, but pretty much, yeah. We're going to see this in the next 3 examples. So, okay, so we have the limit of n goes to infinity here. Now, there is another way of doing this, and we're going to actually use this other method to work out the limits, okay? Instead of having to substitute a very large number for n, we're going to do something a little bit, well, nifty. Now, if we take the limit of n goes to infinity here, but what we can do is take the largest order and divide the whole thing by it. So we can actually do 5n squared divided by n squared plus 6 over n squared over 7n squared over n squared minus 8 over n squared. So we will end up having the limit of n goes to infinity of 5 plus 6 over n squared over 7 minus 8 over n squared. So, if we take the limit top and bottom, this here will go to 0, or tend towards 0, and that will tend towards 0, which will leave us with 5 over 7. So this is dividing through top and bottom by n squared. This only works if you've got fractions, okay, to use this method. If you've just got one line of an equation, dividing each term by n squared won't actually help you much, okay? So we have this one here. We have the limit of n goes to infinity. Now we have an n to the 5 here, so that's our largest order on the bottom. So we've got 3n cubed over n5 minus 10 over n5, 2n5 over n5 plus 1 over n squared Oh, I've just written down the wrong one. Minus 7 over n5. So we have the limit of n goes to infinity of 3 over n squared minus 10 over n5 over 2 minus 7 over n5, which is going to equal to, what do we have on the top? We got 0, so it's 0 divided by 2, so it's going to be 0. Lastly, we have n squared on the bottom, n cubed on the top. If I take the n squared on the bottom and divide through, we will have 8n cubed divided by n squared plus 6 over n squared over 4n squared over n squared plus 1 over n squared equals. So we have limit of n goes to infinity of 8n plus 6 over n squared. So it's 4 plus 1 over n squared. So on the top, when n goes to infinity, what do we have on the top? Infinity, because this one here is actually times by. So we have infinity over, on the bottom we have 4, so infinity. So what this tells us, the terms in the sequence increase without bound. So let's move on to the next. Now, above or on the previous page, we looked at how to predict the existence of limits of certain kinds of sequences, to which the general term was the ratio of the two polynomials in n. Now, when we work through these examples by dividing through the numerator and the denominator by the highest power of n in the denominator, and use the limit theorems from the previous page, we had 5 over 7 for the first one, 0 for the second one, and the limit did not exist for the third one. So the degree of the numerator equal to the degree of the denominator gave us a nice little limit. But when the degree of the numerator was less than or greater than the degree of the denominator, we end up getting 0. So this one has to be less than. So our numerator here is n cubed, and that's n5. So we end up getting 0. Here, when the degree of the numerator is greater than the degree of the denominator, the limit doesn't exist. So this is called top heavy, bottom heavy, okay, and this one's just, the degree is the highest power of n. I mean, if you look at this, mathematics does tend to use human terms to describe things. Okay,